Okay, next topic that we will discuss is Newton's method. So it is used to solve equations which don't have the specific formula or technique to be solved. So for example, we have, let's say, a function x times x plus 2 to the power of, I don't know, 50 minus 1 plus x to the power of 50 as well, plus 5 equal to 0. So this type of function, we don't really know how to solve analytically, or it's difficult, or let's say we have cosine of x is equal to x, or maybe 1 over x equals to cube root of x minus 1, or something like this. So it doesn't necessarily have the way or nice formula to solve for x, right? So in these cases, we will use Newton's method. This is the kind of numerical method that is very useful as a first step, let's say, and then there are other methods, numerical methods, that are more robust, or they provide a bit better approximation for the root or for x, but this is good enough. So most calculators and computers are programmed using this in this Newton's method to solve any equation. So the formula is the following. So we have x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So as you can see, we rely heavily on iterations, and I guess as many iterations, you can do as many iterations as you want to be as close to the actual value as possible. But let's see first an example of how it works, and then and then I will show you how this formula is was derived, and why it is this way and why it works. So let's say we have an example, x squared minus 2x equals to 3. So using the analytic mathematics, right, we can solve this function. We have x squared minus 2x minus 3 equals to 0. We can factor x plus 1 and x minus 3 here. And the solutions are x is negative 1 and x is equal to 3. So this is the way we kind of use usually, right? The analytic way. Now, what if we find one of the roots? I will just focus on one of those roots to do the Newton's method. So if we use Newton's method to find one of these roots, let's say for x equals to 3. So I need to first determine what is my f of x. So first step is determine f of x. In our case, we are given a function x squared minus 2x is equal to 3. So my f of x would be x squared minus 2x minus 3, right? Because we can move everything to one side and equate it to 0. X squared minus 2x minus 3 equals to 0. That would be easier kind of to work with, right? So now we need to find f prime. Second step is find f prime of x, which is 2x minus 2, right? And now third step would be to guess a value of x1. So in our case, let it be x1 to be equal to 2. So it's not a root, right? We know that, but it's some random value that we're guessing. And now using the Newton's method, step 4, we have x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So for the second iteration, so first iteration is x1 is equal to 2. Now second iteration would be x sub n, so the previous iteration, which is in our case x1 minus f of x1 divided by f prime of x1, which is, in our case, is 2 minus f of x1, or f of x would be, so it's going to be 2 squared minus 2 times 2 minus 3. And that's divided by f prime of x1. So into the x prime, sorry, f of x prime, f prime of x, we plug in our 2. So we have 2 times 2 minus 2. And in this case, what we end up with is 2 minus 4 minus 4 minus 3 over 4 minus 2, which is 2 minus 7, negative 3 over 2. And that would be 2 plus 3 over 2, which is 3.5. All right, so this is my x2 is 3.5. All right, now next iteration would be x3, right? To find x3, I need to plug in x2 minus f of x2 over f prime of x2. So I input all the values for x2 equals to 3.5. So in my case, it's going to be 3.5 minus, so actually let me write it first as just a function. So x2 minus x2 squared minus 2 times x2 minus 3. So this is my f of x. And then I divide it by 2 times x2 minus 2. So this is my f prime of x. So now when I plug in values, I have 3.5 minus 3.5. I have 3.5 minus 3.5 squared minus 2 times 3.5 minus 3 divided by 2 times 3.5 minus 2. So I would have here 3.5 minus 2.25 over 5, which is approximately, well, that's going to be 3.05. Okay, so as you can see, we're moving closer and closer to the actual root. Remember that the root was 3, right? So we're at first iteration, we were just a random guess was 2. And then the second iteration, well, first random guess was 2, and then first iteration of the Newton's formula was 3.5, which is closer to 3, right? Next iteration, the second iteration, produces this 3.05, which is much closer to 3. So now if I continue on, for x4, I will have x3 minus f of x3 divided by f prime of x3, which is 3.05 minus 3.05 squared minus 2 times 3.05 minus 3 divided by 2 times 3.05 minus 2. And if you calculate it, you will get a value that is 3.0006, which is much, much, much closer to 3 than the previous iteration. So if you continue doing those iterations further and further, eventually you will get very close to this 3. So I think this is a good way to stop, because next iteration I will have more zeros. So I already see that I'm approaching 3, right? So this is how you can use this Newton's method and formula to approximate where your roots are. Again, you can find one root at a time, and then for the second root, you'll need to repeat the process, choosing some other initial value that is maybe close to 1, or maybe something like close to 0 or -1 or something like this. Okay, now let me show you why actually this actually works. So let's say we have a function like this. So this is my f of x. And now I want to find where the root is located. So let me mark this, oops, let me mark this point as root. So let me put an R. Okay, so if I start somewhere randomly, let's say at x1, that would be my first initial guess. So that's going to be right here. What I do is I draw a tangent line through that point, but then I will need to extend it to the x-axis. Why? Because this is where the root of this line is located, right? So what is the equation of this of this pink line? That is going to be y is equal to f of x1 plus f prime of x1 times x minus x1, right? So this is my f of x1, and this is my x1. Okay, now to find the root of this line, I need equate it to 0, right? So I need to make my y equal to 0. So what I have here is f of x1 plus f prime of x1 times x minus x1. Now, from here on, I need to find the x for the next iteration. So my x2 happens when y equals to 0. So that's going to be right here. So let me mark it with, I guess, another color. So that's going to be my x2. And then I again, evaluate it at the point on the curve and repeat the process again. So I draw this tangent line here, and again I need to find the equation of this tangent line, and my root happens, let me zoom it in a little bit, my root happens here. So this is where my x3 will be, right? So right here, that's going to be the location of x3, where y is equal to 0 for this green line. And as you can see, if I continue on, if I extend that, actually, oops. So if I extend that and draw a tangent line through this f of x3 comma f of x3 point, right? You see that I'm getting closer and closer to the actual R, right? So in this case, I probably need like 3 iterations or so to get to R as close as possible. Now, how do I find the formula for the next iteration? This is where we use the formula of the line starting from this pink line. So this is the formula for the pink line, right? So now I need to solve this function for, again, we said that it's equal to 0. So I need to solve for this x. So what do I have? I have f prime x of x1 times x minus x1 is equal to negative f of x1. Now I divide everything by f prime of x1. So these are gone, and I have x minus x1 is equal to negative f of x1 over f prime of x1. And now I just need to move this x1 to the other side, and I have x is equal to x1 minus f of x1 over x prime of f prime of x1. Okay, and we said that this is going to be our next iteration. This is going to be my x2. So if you repeat this process, you'll see that eventually you'll land to this formula xn plus 1. The next iteration of x is x sub n minus f of x sub n divided by f prime of x sub n. And that would be the general formula. So each time you start somewhere and then you draw a tangent line, you find the root of that tangent line, you evaluate it at on the curve, and then that's going to be your next iteration. You again draw a tangent line through that point, you find the root of the tangent line. That would be your next iteration. You evaluate it at the function, and then you again repeat the process again and again until you reach that R. So now we would say that if R is the solution of f of x equal to 0, then R, the root, right, the actual root, is equal to the limit of this x sub n as n goes to infinity. So you might have to have a lot of iterations until you reach the actual value. But in our cases, usually like 3-4 iterations will suffice. Will not have anything too difficult. Now, there is a caveat here. So there are cases where Newton's method might fail, and let me show you those cases. So let's say if I pick a point as my x1, something random. So let's say I have this function right here, this curve, right? And as you can see, the root is located here. So this is where I need to land eventually, right? However, if I pick a point x1 randomly to be, let's say, this one, right? And then I draw a tangent line through this point, it would be something like this, right? So if we extend it, because for the next iteration we need this line to touch the x-axis. So if I extend it here, as you can see, so this is where my x2 will be, right? And as you can see, if I evaluate it here, what I see is that I am essentially getting to the local maximum, right? So this is where my f prime of x2 will be equal to 0. And that's a bad thing, because remember, when we have a formula, x of for the next iteration, x3, that would be x2 minus f of x2 over f prime of x2. So as you can see, when we evaluate f prime of x2, we get 0 here in the denominator, which should not happen, right? We cannot evaluate that. That is undefined. So you can, in this case, just have a random value x1 that you pick yourself, and then you do just the first iteration. And this is where you essentially you stop, because you cannot continue. But this is very far from the actual root, right? So you need to be careful with what values you choose for your first initial guess. So this one might not work. Maybe somewhere close here would work better, or I don't know, somewhere here. So you'll need to be careful with that. Another example is the following. Okay, so let's say I have the function like this, and clearly the root is somewhere at 0, right? But if we use Newton's method and we pick a value that is, I don't know, our initial guess is somewhere here. So we will need to draw a tangent line through that point. And we see that it's gonna be, oops. We see that the root happens here, right? So if we extend it, we don't have to extend it like too far. So this would be more than enough. So this point right here, that's gonna be my x2 for the next iteration, right? So now from here, I need to draw again a tangent line through that point. So that's going to be, okay. So that's going to be somewhere like right here. Okay. And then the root happens where y equals to 0. So my next iteration would be x3 would be here. So when I evaluate it and I draw a tangent line through this point, I see that it is, as you can see, it kind of moves even further. Something like this, right? So my next x4, next iteration x4 happens very, very far right there. So as you can see, we're moving further and further away from the actual root. So we started pretty close from the root. That's my x1, the initial guess. And then I do the Newton's method. That's my x2, which is a bit further from the root than x1. And then I evaluate it. I repeat the Newton's method again, and you see that I'm even further now on the next iteration than I was before. So my initial guess was even closer than after applying Newton's method a couple of times. And then as you can see, we are moving further and further away from the actual root. So this also might happen. So this is where the Newton's method fails. So when you see that it kind of moves further away from the root, or when it diverges, this is where it's a good idea to stop and maybe choose another initial value or change the approach. Now let's look at another example where we can use this method. So let's say we have cosine x is equal to x. This is the example that we saw at the very beginning. And why not to try to use the Newton's method to see if we land on something, right? If we can find the actual solution or root. So the first step is to find the function, right? So the equation can be written as cosine x minus x equal to 0, or we can write it as x minus cosine x equal to 0. Doesn't really matter, right? Both are the same thing. So let me choose, I don't know, the second one. So I choose my f of x to be x minus cosine x. Now the next step, remember, we need to find also the derivative because that's needed for the formula. The formula is x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So we need to have the derivative. So derivative of x is 1 minus derivative of cosine is negative sign. So that's going to be plus sine x. So this is my derivative. Now choose x1. So let's say I have okay, so x1, how can we choose if we're not given any restrictions or the domain or interval or anything? So a good rule of thumb not to be far away from your actual solution would be to draw a cosine function and x function and see where they approximately intersect. So cosine would be, so here we have 1, we have here pi over 2, pi, and the cosine function would look something like this, right? So it's y equals to cosine x, and my function x equals y equals to x will look something like this, right? So that's y equals to x. Now, as you can see, the two functions are kind of intersect somewhere around 0 and pi over 2, right? So that would be kind of an indication of where our first x1 could be. So we know that pi over 2 is approximately 1.57, right? So if I choose x1 to be equal to 1, I think that would be not a bad choice. So let's start with 1. it is pretty close to pi over 2. Okay, so first iteration, x2 is x1 minus f of x1 over f prime of x1. So let's see what we have here. We have 1 minus f of x1, that's going to be 1 minus cosine 1 over f prime is 1 plus sine of 1, right? So if you plug it into calculator, you would get approximately 0.7503639, approximately like that. We can probably just use the 3 digits after the decimal point. Now next iteration would be x2 minus f of x2 over f prime of x2. So in this case, x2 is 0.750 minus x, which is 0.750 minus cosine of x, which is cosine of 0.750 over 1 plus sine of the 0.750. And if we plug it into calculator, we'll see that that's going to be approximately 0.739112 approximately like that. So you see that the digits are still changing, right? So that would be probably a good idea to continue. So you will be given either instruction to repeat the iterations until you have the the first 3 digits are the same, or that you're approaching some value. So let's continue on, and we have x. Next iteration x4 is going to be x3 minus f of x3 over f prime of x3, which is 0.739 minus 0.739 minus cosine of 0.739 over 1 plus sine of 0.739, which is approximately 0.739085133. So I would highly recommend you to, when you use a calculator, to not round it like I did here, because that would maybe create some, bigger error. So try to keep as many decimal points as possible, decimal places as possible. Usually 6 would be more than enough. Sometimes it's 4, but for the sake of just demonstration, I use the 3 decimal places. And this is my next iteration. And then if I continue on and do the 5th iteration, that would be also approximately 0.739085133, which is kind of the same as the previous one. So I can conclude from here. So if I do more iterations, that will not help me because I still approach this value, right? So I can conclude from here that therefore x is approximately equal, so my root is approximately 0.739085133, or in this case I can round it to 3 decimal places, and that would be it. So this is how you can use the Newton's method to approximate your solution. Thank you.